So if we take a little closer look at our implant right now, it's made of two components. One is this 3D woven textile that you can see behind me here. And there's also this true 3D printed component of our implant. And I'm going to touch on each of these here in the next few minutes, but this 3D woven structure is pretty awesome. We're weaving in 3 dimensions, but it can be made to match any joint contour of any shape, and it can be precise and match that joint contour exactly in the body without losing the ability to form cartilaginous tissues or losing any of the mechanical properties. And we published that in PNAS several years ago. And then we're using this true 3D printed structure as well too, and I'll cover that in more detail. And really the technology that we're using here, it's an FFF style printer, but that we're using this to match the precision that we can get with this textile component. And so if we go back to some of the early days of Cytex Ortho and what we were doing, even when we were in graduate school at Duke University many years ago, we had this 3D orthogonally woven scaffold idea. And here I'm showing you the loom that was developed while we were at Duke University. And it's got 400 fibers that are going into this matrix. And if we look at the cartoon form of this and kind of understand the schematic of what we're doing, this is 3-dimensional weaving where we have these X fibers in green, we have these yellow fibers in Y, and then the Z fiber, as you can see here with my laser pointer, consolidates this whole matrix. And so from an engineering standpoint, what we did that was new and what we brought to the field of tissue engineering for cartilage is that by controlling the materials, the yarn diameters, and the spacing along each axis, we can start to dial in the mechanical properties to match those of the tissues that we're trying to replace in the body. And our first publication was in Nature Materials showing that we could tune this structure to match the mechanical properties of articular cartilage. And this is also an implant that can be made very large so we can start to treat the osteoarthritic disease. Another important component of this is that it's porous throughout the matrix. So we're communicating with cells and we don't have any fluid flow or problems or getting nutrient diffusion throughout the scaffold. So this is around a 500 micron hole that you can see here. So cells will find this plenty large enough to dive in, infiltrate, differentiate, and start to produce cartilage matrix. And so you can show here, and I showed you one of these images earlier, but because we can form this to any anatomic shape, here's the shape of a condyle where we've developed cartilage tissue on it, and here's the shape of a femoral head, and we've done the cartilaginous tissue development on that too with stem cells. And so here's probably the largest confocal image you've ever seen. This is a 5mm scale here, and we've stitched together multiple confocal images where we labeled these stem cells with a fluorescent green protein that's live. So showing the cells and how they interact with this textile. And if we zoom in on some of these pores, you can see how the cells are interacting with this. And we've done surface treatments to this structure so that we encourage the cell interaction. And here's a type 2 immunohistochemical label for type 2 collagen, which is the principal cartilage protein in the cartilage matrix. So we showed that we can create this cartilaginous matrix from top to bottom that's consistent with the native healthy tissues.